All right, hi everyone. Thanks for coming. It's good to see everyone here. Eager to learn about R. Excited to be here with you guys. So at this conference, there's quite a few interesting R talks. I think today in the morning, Felix had a talk on structured streaming with R. I actually missed it, but hopefully you guys went and had a lot of fun. Javier, who is the main maintainer and developer of sparklyr, which I'll talk about a lot today. He has a full 1-hour tutorial tomorrow, which should be a lot of fun. So definitely try to go to that. And Hussein, I think, has been the primary workhorse behind sparkr for quite a long time. And he's doing a full session on debugging sparkr tomorrow afternoon. And Navdeep from H2O will talk about the R sparkling API as well. So make sure you go check out all those R talks. All right? It was good to see the Spark and R communities coalescing somewhat. All right, so you guys probably are here because you love R just like I do and can't get enough of R. But if you aren't sold on R yet, hopefully I'll try to sell it to you today a little bit. R has grown a lot in popularity in the last few years. It used to be primarily used in academics, but it's good to see a lot of industry backing behind R now in the enterprise. When I was getting out of university around 2013, I was being warned by my professors that you shouldn't specialize in R because no big shops will hire you if you know R. They want to know SAS, they want to know stat or something. And I was really sad. I had to learn some SAS. But fortunately, I've been able to make a career out of knowing R. So that's kind of cool. Since 2013, the IEEE rankings have kind of shown R boost in the rankings. So in 2014, R was number 9 in the rankings. And then the year next, it was number 6, just behind C# and Python. And then last year, it was all number 5, actually above C#. So as a R developer at Microsoft, that's kind of a big boost for us. All right, so what is R? It's a statistical programming language. So it's designed to do a lot of data analysis and statistics. Has a lot of really powerful packages for visualization and modeling. And it's entirely open source. So there's a really good community behind R contributing towards it and making it a very performant language. The community is always growing, and it's always getting more interesting to see people adopting R for different use cases. It used to be primarily in academia before, but now you can see a lot of industry uses of R as well. Actually, Airbnb just had a talk today, and I saw them at a small R conference earlier this year, and they had a really, really cool demonstration how they use R a lot for their sort of award-winning hosts metrics, so on and so forth. So it's pretty cool. So there's over 10,000 packages available on CRAN. So CRAN is the central R archive network. It's a hosting service for R packages, kind of like PyPI for Python. There's over 10,000 packages up there, which is pretty impressive. You know, these are all packages designed primarily for data analysis, visualization, and machine learning. So for a pretty unique domain, it's kind of interesting to see how many packages available for it. But taking a step back, I think of R as an interface. Actually, there's a book that came out, I think, just last year by John Chambers, who was one of the primary developers of the S language, which is where R's inheritance came from. And he made a lot of effort in this book to describe how R was designed to be an interface language, and that's what's really best at. J.J. Allaire had a really cool quote. He said that you should understand R, or think of R, as a user interface, or a language that's capable of providing very good user interfaces. Right? So R was designed from its ground up to be a user interface for Fortran and C code. So it's a very cool way of linking to those libraries to do heavy lifting for data analysis. So Hadley was quoting Joe Cheng, who's the developer of Shiny, and he has kind of an interesting quote. He says, R is not a DSL. It's actually a language for writing DSLs, which is altogether more powerful. That's a little too meta for me, I think, but I think the point is, when you use R to do these cool interface things and develop DSLs with it, it's really impressive how much expression you can put into R as a language. All right, before I dive into what I want to talk about, I want to at least describe what the Microsoft R distribution of R is, because it's not always very well explained. So the original distribution of R is the CRAN R, or GNU R, which has been available since the early 90s. It's GPL licensed, single-threaded, and entirely in memory. So all your computations will take place on one core. Everything you create in R as an object will reside in some memory address. It does have over 10,000 packages. Sorry. So some of those packages will hopefully allow you to interface different environments, like databases, so on and so forth. But for the most part, all the lifting you do in R is happening in memory. To get truly performance, it was actually designed to be an interface for C and Fortran. It's a very, very good interface with C++ using RCPP, and you can get better performance that way. It is cross-platform, so it works on Linux, a lot of distros of Linux, including Solaris, Ubuntu, so on and so forth. It's also available on Macs and Windows. And that's kind of why the R core team really emphasizes compatibility more than adding new methods to it. So that's kind of why it's stuck in this sort of role, even though some of the things are kind of limitations. One simple improvement that you can do in R is bundle it with better linear algebra runtime. So what MRO is the Microsoft R Open distribution, and it takes the MKL library from Intel and bundles that with the R distribution. So that way you get automatically multi-threaded linear algebra runtime. So if you have a matrix factorization operation or multiplication, it'll work on more than one thread. So that's kind of cool. It's still fully compatible with CRAN, so any CRAN package will just work out of the box. You don't have to rewrite any code. So it's just an automatic boost in performance just for installing it. It also comes with a package called Checkpoint, which basically takes a snapshot of CRAN every single day and hosts it on one of our servers. And that way, if you use a package from CRAN and the author of that package decides to change something and break your code, you can revert it back to the earlier date. So it's kind of a simple way of doing reproducibility. It's also open source, MIT license, just taking the R bits and bundling them with MKL. I think Intel is going to be very similar with Python. They have their own Python distribution, just distributed with MKL instead of OpenBLAS. OK, because it's our server, it should have a client. So our client is a client for our server, which I'll describe next. And it's basically MRO plus a set of packages for more performant analytics. So the two packages are Microsoft ML for machine learning and RevoScaleR for scalable analytics. These two packages will allow you to use more than one thread. All the computations on these packages will use as many cores as possible. But for our client, it's not meant for deployment or production. It's meant for prototyping. So you get to use two threads to make sure it actually does parallelize, but it's not meant for actually creating a deployment solution. When you want to deploy your solution, you use mRes deploy, which is another package to deploy that into a server instance. This is available for free, so it's not open source. The two packages, RevoScaleR and Microsoft ML, are proprietary, but you can get it for free to try it out. It's basically MRO plus those two packages, but all in memory. And it's available for free on Windows and Linux. And I have a Docker image of it on GitHub if you want to try it out on a Mac if you don't have a Linux system lying around. So these three distros are all in memory. So you won't get parallelization off the memory process in your computer. So this is how you made Microsoft R Server, which is a out-of-memory, completely unshackled distribution of R. So the two packages we have, the Microsoft ML package and the RevoScaleR package, they will scale out to every compute resource you have in your system. So if you're working on a local machine, you'll use all your threads. If you're working on a Spark cluster, as we'll see today, you'll use all the executors in your Spark cluster. In order to really get that true out-of-memory and distributed opportunities, we have a new data store called XDF, which is kind of like a Parquet data structure. It's a column-oriented data set that's chunked by rows. And it can be saved in HDFS on disk locally. It's an enterprise product, so you get commercial support. So if you hit a bug, you can get someone off vacation and fix it for you. It's available in Linux, on Red Hat and CentOS, as well as on Windows, Spark, Hadoop, and Teradata. All right, so this is where you get the true out-of-memory, multi-core, multi-node parallel algorithms. That being said, I think we're all here to talk about Spark. So that's just one of the Spark APIs. There are three APIs, which were also being talked in the other talks I mentioned in the beginning, are these three APIs here. The most, I guess, the cornerstone of these three APIs is the Spark R API, which is what comes to Apache Spark says 1.4. It's Apache licensed, so it's completely free and open to use. It gets Spark SQL and Spark ML support directly through an RPC connection to your Spark cluster. I guess today, Felix showed you how to do structured streaming, which is pretty exciting. But as far as I know right now, the core usage is Spark SQL and Spark ML. That being said, because it's a direct RPC layer to your cluster, you also get a pretty impressive mechanism for doing your own distributed functions across your cluster. So if you have your own R function, you want to distribute it across your cluster, across each partition of your data frame, these three functionals allow you to do that. So you take some existing R code, it'll get shipped to the cluster, each partition will get serialized into an R object, run the operation, and give you results back. The one that came out last year and made me super, super happy, more happy than any API should make you, was the sparklyr API that came out of the great folks at RStudio. and it's on CRAN now. It's also on GitHub. It's very actively developed, and so it's always good to see what they're working on. It has support to Spark SQL and Spark ML through DBI, which is a database interface in R, dplyr, and RPC. But I'll show you the really cool thing about it is dplyr has a really expressive mechanism to talk to remote databases. So you certify dplyr code, and it just works in Spark automatically. And it's really impressive how native and how easy that works. UDS support was announced, I think, just yesterday, so this is hot off the press. Make sure you check out Javier's talk. I'm sure he'll show you all the cool things there. But they've added support now to do similar to Spark lapply, but all through sparklyr. And I guess the goal for that is hopefully we'll get sort of syntactic sugar ways of doing things in an R way, like using per and other R packages, which I'll describe in a second. It also interfaces with Livy, which is another REST API for Spark. So you can execute Spark applications, but from a local environment. So you're on your local desktop, you fire up RStudio, use Livy to connect to your Spark cluster, and send your applications there. So that's kind of cool. And by far the best thing about sparklyr is its mechanism for extensions. It has a really native and easy way to make extensions in sparklyr. Everything I want to talk about today actually goes down to it some way. So it's really cool, really fun. The RevoScale-R API, I'm calling RxSpark, but we don't really have one branding for it. But this is the API you get through the Microsoft R server implementation. And this has interoperability with sparklyr. So if you use sparklyr, or I actually don't know what to call it, sparklyr or sparklyr. I feel bad saying sparklyr because I'm calling Spark a liar, which we know it's not. But you get interop with sparklyr, so you can create one Spark session and use both the APIs together. Right? You can't do that with Spark R right now. I think on Databricks Cloud you can, but in most ER instances of Spark, you can't share Spark sessions from sparklyr and Spark R. RxSpark can consume Parquet, Hive tables, and all kinds of data sources, so it's pretty easy to walk back and forth between the two APIs. And we have really robust support for UDFs in many different ways. So we can apply R functions at the chunk level. So if you just want to do add a new column or manipulate each row individually, you can do that pretty easily with RDataStep. If you want to apply a function to each partition of the XDF, or if you want to apply it to each group from XDF, you have functions for that as well. Currently it's on version 9.1, so that's the R server versioning. OK, so let's dive into what actually happens. In a local compute environment, MRS will actually use all the cores you have in your system. In order to go beyond your memory limitations, it will use the hard drive for its data, not the RAM. On a cluster, you get even better utilization, so you get to use all the available nodes. So if you have a Hadoop or a Yarn or a cluster, use all the nodes you have there. And instead of saving things on disk, go save in HDFS. So it really scales out the way Hadoop scales out. To change the environment is super simple. You just say, hey, I want to change from a local parallel compute context in this environment to a Spark compute environment. Just one line of code, and everything else will automatically get distributed in the new environment. So nothing to configure, no need to rewrite any of your code. Every additional MRS function will get automatically implemented in the new environment. OK, so how does it work? All the MRS functions, which are prefixed with Rx, are parallel external memory algorithms. So they're parallel because they're working on multiple executors, multiple processes. And external memory because they're not in memory, they're on disk or HDFS. But whenever you call them, each process will pull in some chunk of data from HDFS or from wherever it's stored, process that, calculate some intermediate result, and then give you a summarized result at the end. So just like how any sort of distributed environment would work. But because we have the R client and our server instance, this is a pretty friendly approach for doing server-based installations of MRS. So for example, you could have a local computer running R client, where you might prototype a solution just using your local CPU threads. And then when you're ready to deploy it into a cluster, you just use the MRS deploy package and say, hey, ship this script or this function and put it on my cluster. And in that case, the cluster will create a Spark session for you. It will use executors to run all these Rx jobs, summarize them for you, and get it back to your client. Right? So you get a really extensive mechanism for doing distributed jobs. There's a whole lot of algorithms that are available in the two packages, RevoScale-R and Microsoft ML, and they're all external memory parallel algorithms. So a lot of stuff for just regular data processing and ETL type workloads, but also a lot for statistical workloads. So before before we actually marketed our server, we were a shop called Revolution Analytics, and we focused on a lot of statistical learning, statistical methods. And so we have a lot of statistical tools in there as well. But we have added through Microsoft ML a bunch of high-performant machine learning algorithms, including neural networks, convolutional neural networks, gradient boosted trees, random forests, so on and so forth. OK, so in order to actually create a Spark session that you can share through MRS and through Spark, Lyr is pretty simple. Before I showed you RX Spark and then set compute context to that. But a simple way of doing it is just doing RX Spark connect. All right? And here, the only parameter you'll pass to it is say interop equals sparklyr. And this tells MRS that create a session and register that session for sparklyr as well. And the extension mechanism of sparklyr will allow you to use any sparklyr extension package, like our sparkling, for example, in the same Spark session. So you can, anything that's available in sparklyr or its extension library will work here as well. So we have one variable called cc that will let MRS know how to point to a Spark session, and then one variable called sc, so sparklyr will know how to point to the Spark session. They both point to the same session, just two different variables for each environment to work with. All right, so why did sparklyr make me so happy? Well, the reason is our community has made a lot of really cool tools to make data analysis just fun and expressive and easy. Most of this has happened in this new coalesced environment called Tidyverse. And the Tidyverse is just a bunch of really, really fun and really useful packages for doing data analysis and visualization and even modeling. So the most prominent one is probably the dplyr package, which is a package for doing data manipulation and aggregation. It was meant for working with local R data frames, but it had a mechanism to talk to remote environments like SQL databases, BigQuery, so on and so forth. And a bunch of other packages. Perhaps the cornerstone of all these packages might be the Tibble package, which is kind of weird. But Tibble or table is kind of an abstraction for data types that can be read in this environment. Right? So we'll see Tibbles quite a bit. Tibble is this cute way of saying table, I think. Right? And all these packages take a fairly functional approach. So they want to do things that are expressive and efficient, but also don't create too many weird side effects that you can't replicate afterwards. So that kind of works really well for Spark, because Spark is based on a functional programming language as well. So having this functional paradigm works very well. And even though sparklyr sticker is not there, I really think it's part of this tidyverse of packages. And this would be our sort of glue from Spark into tidyverse and vice versa. So we can sort of borrow ideas we've learned from the tidyverse ecosystem for EDA and modeling and use them in a Spark environment. OK, so in order to kind of understand how to fit these together, let's talk about some Spark abstractions for R. So how core constructs in Spark relate to objects that might make sense in R. So the only four I'm going to think about are the data structures and the functions that we use in data structures. So we're all familiar with what the core generic data type is in Spark, and then what kind of operations you run on them. These don't have exact replicates in R, but fortunately, there's some really close analogies we can put into our heads. So RDD in R will probably be a distributed list, right? So a list that's not just sitting in one location, but a collection of objects sitting in a cluster, but generic objects that could be anything. If those things had a very fixed schema, then there would probably be a DataFrame. And for R, that would be a distributed data frame, right? So this would be our main pointer into the Spark ecosystem from R. So we'll just look at this DataFrame object and call it a table something, right? In our case, it'd be a Spark table. Also be a lazy table because it's Spark. And because it's usually running Spark SQL, for data frames, we have Spark SQL going through to this as well. All right, instead of creating new operations to work with Spark from R, we'll just borrow a lot of dplyr mechanisms and methods to call on Spark directly, and transformers from the ML pipelines package and other things that aren't in dplyr we'll just have connections for. I am running out of time, so I'm going to speed up a little bit. So here's an example of what happens. If you look at this, it looks a lot like R code, because it is R code developed by R developers. So it's really much like what you would see in any R package. It's actually the syntax you would see in another tidyverse package called readr. So here I'm using that SC object, which is a pointer to the Spark session for sparklyr. And I'm saying use that session to read a CSV object. And that CSV object is saved in HDFS directory called users under some data directory. And it doesn't have any header row. And the Spark SQL table should be users. So in R, we have a variable now called ghusers, which is the R object pointing to some Tibble object. And in Spark, there's a Spark SQL table called users, right? So it's a really clear connection between what's happening here. And the attributes of users is a tibble, so no matter what, dplyr knows what tibble is. So it won't ever say, hey, I can't deal with that, because it knows exactly what tibble is. But it also has more important attributes. It's a lazy table, which is useful because it'll tell dplyr, don't get eager with the computations here. Just compile them and then hand them off to SQL. And the SQL should be running in Spark, right? So it's given dplyr a very clear mechanism how to do these operations. All right. So for example, if you had some local R codes, so here's just a local R data frame, not a Spark data frame, but a local R data frame, which is a sample of the entire database I'm looking at. Which I'll talk about more tomorrow, which I don't have time for today, but it's a really cool data set. And I'm basically grouping by language and summarizing for each language the unique number of committers to that language, and then summarizing it. And there you go. That's your tibble. It's a local R data frame. The exact same code I can run in sparklyr using the same dplyr methods, and it works. But now it actually goes to Spark. It makes a SQL statement for me, submits it to Spark, and everything happens in Spark using all the cool optimizations, all the tungsten, all the catalysts, everything happens there. So those aren't sparklyr functions. If you look at the sparklyr source code, you won't find the group by there. It's actually a dplyr method, typically for the tibble SQL class, and then gets sent to Spark. All right, so for example, you could use the explain function and sort of see the code gen coming from Spark, coming from actually dplyr to make the SQL statement, and then you could even say verbose equals true to see what's being converted to physical plan for Spark. And you can go a lot further with this. So dplyr has a really powerful mechanism for doing data manipulation and aggregation. So you can do joins, two-table joins, a lot of expressive things directly in R, and using a really expressive R syntax, right? This is kind of how you would think of R code: take a table, do some filters on it, and then join them. And now the cool thing for me is I don't have to worry about optimizing my actual calls. This will go to Catalyst, and it'll figure out the best way of optimizing this for me. All right, so that's cool. I think that's the Spark SQL piece that we've kind of solved directly using dplyr and sparklyr just automatically. It's kind of impressive. But let's look at MRS for the computing side, because some pretty cool things coming out of MRS on that side. So the two packages I talked about, ReloScalar and Microsoft ML, were two packages. The first one is written primarily in C++. So it's everything you call there will get compiled down to C++ environment. Microsoft ML is actually a Microsoft package, so it's primarily written in C#. There's some C++ in there. So we have a bridge from the MRS server, which is where most of our things run. It's called BXL server, into the C# library, and then vice versa. They're both parallel external memory algorithms, so you can automatically scale out to multiple nodes. So our sort of way of getting around our session using the two libraries will be to pass it through to some data source that can be consumed by both. We don't directly consume Spark data frames because we already have a very efficient format for data structures, and it's a format that R and C++ can understand, not a Java-based object. So it's always preferable to write out something like Parquet and Hive and then read it into MRS. And those are the functions you would use on both sides. You could write to CSVs as well or something else, but these are probably the better formats to use. All right, and in MRS, we have a bunch of really performant algorithms for doing distributed modeling. So we have neural networks available. So for example, I'll talk about this again tomorrow more, but it has this really cool data set of GitHub. It's basically a big dump of all of GitHub, a big, retrieval of all of GitHub. And it basically has every user, every repo, every commit, every code difference, and every message and pull request. So pretty much everything in GitHub, right? And what I'm trying to do here is I'm trying to see what's the probability that a pull request will be accepted given that code patch, right? It's kind of weird, but what's cool about this is Microsoft ML will do all the cool tokenization for us, all the cargrams for us automatically. And this would be a pretty hard operation to do in R, and Spark has good sparse matrices, sparse vectors, but encoding that in something R can understand would be kind of difficult, right? So MRS will do all this really, really efficiently for us in distributed fashion. So there are two algorithms. That's neural net happening. That's a fast trees, which is kind of like gradient boosted trees. But also what's pretty powerful is you can do your own ensemble algorithms. So rather than relying on a gradient boosted tree or random forest, if you want to train your own ensemble classifier or regression model, you can do that as well. So the function call is RxEnsemble. You'll tell it what formula you want to estimate and some data to estimate it on. And then you say what kind of trainers you want. All right, and trainers are just the algorithms we already have. And it's a very efficient way of describing the ensemble because the parameters that go into any given algorithm are part of the algorithm's function of arguments. And you can do sampling on the features and on the data as well. So it's a good way to develop diverse classifiers or regression models across the data set, right? And it's just 6 lines of code. Actually, it's 1 line of code you put into one really long line, but it's just one really simple function call to create a pretty awesome ensemble. The other thing you can do pretty easily in MRS is hyperparameter optimization. So just like you can do with cross-validator in the pipelines package, we have mechanisms for distributing calls across different values of an argument. So for example, here you can do sort of cross-validation where you're doing for k different folds. I mentioned that you can do UDFs at the row level pretty easily with Arc data steps. So here I'm saying for each row, pick it if it belongs to I. And I is what I'm actually applying the functional on. Right? So it's going to do k different folds. Each fold will only have that specific one for that specific operation. And for each is a pretty robust parallelizable backend. So it supports many different environments, including local parallels, all your CPU threads. It supports Redis, so on and so forth. So if you write this code for one environment, it'll work automatically in different environments as well. One example, for instance, is we just announced Azure Batch, which is a low priority, like sort of spot instances for doing parallelization automatically, which is kind of cool. All right. OK, also we have pre-trained algorithms for both vision and for text. So if you already have a data set that you want to, like a big vision collection of data or images, we have pre-trained models for AlexNet, for ImageNet, using the ResNet algorithms, which won ImageNet a couple years ago. So really, really long, big topologies for neural networks. And made it pretty easy to just apply that pre-trained model to your own data. So for example, here I'm saying, here's a data source called train, and I'm going to calculate these features from the raw pixels of my own images using the pre-trained weights from the ResNet model. Right? So the DNN model I'm using is the ResNet model here. So rather than doing anything complicated, it just sort of automatically happens, and it'll distribute across your cluster as well. So you can save your images across HDFS. Each of them will get called up. You get automatically a pretty cool model. OK, my last 2 minutes, yikes, I'll talk a little bit about some really cool extension mechanisms coming in Spark. So I think you already saw that we have a really, really powerful method for dplyr using real natural R language, right, using dplyr. So that's pretty cool. For ML, we both have Spark ML, H2O. Definitely go see the talks tomorrow by Navdeep and Javier, more about those things. But we also have all the cool ML functions in Microsoft R Server. There's 2 pieces that we're kind of missing, so I've been really hoping that we could get this together, and we've made a lot of progress there already. So for Spark Streaming, we have a package called Spark Streaming, and it will apply the RDD-based streaming API and give it to you using an R interface. So here, for example, I have a data source, and stream records will read the data source and put it into a Hive table. So if I look at that, and I'll be appending to a Hive table that I can utilize later on. So I stream the records, I got the Hive tables, and now I can run, for example, a model on the updated Hive table. We haven't added any online algorithms. I think the next big step for us is think about good ways of adding online learners to incoming data. But at least now we have interface from R to the streaming API. And I'm working on a structured streaming API, which I have to admit is pretty fragile right now. So something hopefully I get time this summer to work on, but it's also pretty cool. Thing that I'm trying to figure out, and something, if I can find Javier somewhere, I'll ask him about it too, is a way to figure out how structured streaming might fit with the already existing dplyr modules in sparklyr. Right now, I've created new methods for him, and you have to specify everything kind of manually. And here I'm running the stream out to a Parquet file I get appended to. And then for graph frames, I just saw a couple weeks ago that Kevin Kuo, I don't know if that's the last name, hopefully I'm not getting it too bad, created a really cool package called sparklyr graphs based on sparklyr. All these packages I mentioned right now are based on sparklyr. So that's kind of the cool thing about sparklyr is it makes it super, super easy to create efficient mechanisms for Spark from R. So he created one for graph frames, and you automatically get all the cool DataFrame-based graph modules in Spark, in R. All right, I made it somehow. Thank you.
OK. OK, we're kind of low on time anyway, so you can find Ali offline.